Hello everyone. In this video, we'll be covering concepts from the course of Chemistry 1411, also known as General Chemistry 1. The topics that we're covering today are going to be gas characteristics and the gas, also known as the ideal law. The gas laws. The gas law describes behavior of gas in terms of 4 variables. It's going to be pressure, temperature, volume, and moles. The pressure will be P, temperature T, volume V, and moles is going to be the letter N. An ideal gas is a gas that exhibits linear relationships among these variables. And we'll be able to see that using this equation. So it's PV equals nRT. So pressure times volume equals moles times R times temperature, and R is going to be our constant, so our gas constant. So this is the equation. You just kind of manipulate your ideal gas equation at standard temperature and pressure, and you get this amount. So 0.0821 is going to be your R constant. So that is the value that you're going to use with the unit of ATM times liters divided by moles times Kelvin. So this is what you're going to plug into that R spot when you're solving an ideal gas law equation. And then we're going to cover, in depth, we're going to cover Boyle's law and Charles' law, but there's also one called Avogadro's law. So let me go ahead and give you a brief little overview of both, and then we'll go into Boyle's and Charles a little bit more in depth. So when we have a fixed number of moles and temperature, we can find Boyle's law. So Boyle's law, our volume is going to be equal to our R constant divided by our pressure. For Charles' law, when your moles and pressure are fixed or constant, we have volume equals our R constant times temperature. And then finally, for Avogadro's law, with a fixed pressure and temperature, our volume is going to be equal to our R constant times our number of moles. So let's go and relate our Boyle's law and Charles' law. These two are going to help you better understand the relationship between the variables that we actually use in the ideal gas law equation. So the first one is going to be Boyle's law. At constant temperature, the volume occupied by a fixed amount of gas is inversely proportional to the external pressure. So we're going to have a fixed temperature and fixed number of moles. And we're going to see how pressure and volume will react to each other. So it says it's inversely proportional. This means as one increases, the other variable will decrease, and vice versa. So we can see that as we decrease our pressure and increase our volume, so by increasing our volume, we're lifting the lid up, and it also will relieve some of this pressure. So the pressure will also decrease. So by increasing our volume, our pressure will decrease. And then it's the exact opposite for our other picture. So as we push this lid down, we're increasing our pressure because it's getting a smaller amount of space, but it also means that we're decreasing our volume. And that's kind of what Boyle's law is saying. So our pressure and our volume are inversely related to each other. When we get to Charles' law, it states that at constant pressure, the volume occupied by a fixed amount of gas is directly proportional to its absolute temperature, and this is going to be in Kelvin. So it's saying that we're relating our volume and our temperature at a fixed number of moles and a fixed pressure. So we're not changing the pressure, we're just changing the volume and the temperature. Because it's directly proportional, this means that as one variable increases, the other will also increase. As one decreases, the other will also decrease. So we can see this in these two pictures. So with temperature 1, we have a decreased volume, but we also, by looking and comparing the two, we see that our temperature here is lower. When we come over here, our volume has increased, and our temperature has also increased its amount. So as one increases or our volume increases, our temperature increases. As our volume decreases, our temperature will decrease. And this is going to be Charles' law. And now we're going to talk about standard conditions and a gas behavior at those conditions. Standard conditions are going to be referred to as either STP or standard temperature and pressure, which that's kind of what the STP stands for. So standard temperature and pressure. You're going to see this on, you could see it on your homework, your exams, that kind of thing, any practice. It just simply means they're going to have a constant value. So if you're looking for a specific variable, you simply plug in all the known variables and solve for what you're looking for. So at STP, or standard temperature and pressure, your pressure is going to be equal to 1 atm, or you can say 760 torr. Your temperature will be either 0 degrees Celsius or 273 degrees Kelvin. Your your moles will be equal to 1 mole, and your volume will be equal to 22.4 liters. So as you can see, your pressure is in atm, your temperature is in Kelvin, your N is in moles, and your volume is going to be in liters. So let's go ahead and work through an example. This example states that 2.3 moles of helium gas are at a pressure of 1.70 atm, and the temperature is 41 degrees Celsius. What is the volume of the gas? So we're given moles, pressure, and temperature. We're looking for volume. So let's go ahead and move over to our boogie board and we can work through this example. Move my mouse for you. All right. So we know the ideal gas law equation is PV equals nRT. But we want to rearrange this equation to be able to get us what we're actually looking for. So by dividing by pressure to get volume by itself, we end up with volume equals nRT divided by P. And now we just need to identify what all our variables are equal to. So our pressure is going to be 1.7 atm. Our volume is what we're looking for. Our moles are 2.3. Our R is going to be that constant, so 0.0821, and that's liters times atm divided by Kelvin and moles, or moles Kelvin. It doesn't really matter which one you put first. And then our temperature is 41 degrees Celsius. However, we need to convert this from Celsius to Kelvin. So if you're trying to find Kelvin, you're going to take your degrees Celsius and add 273 to be able to get our actual temperature in Kelvin. So when we say 41 plus 273, we'll get a temperature of 314 Kelvin. And that's what we're going to use for our temperature. So now we can go ahead and plug everything in. So we can say that volume equals our moles, so 2.3 moles times, I'm going to go ahead and put my R towards the end. It just makes it a little bit easier when we're canceling out. It just makes it a little prettier. You'll be able to see what I'm talking about when you see me cancel out units. So I'm going to go ahead and put my temperature next. So 314 Kelvin times 0.0821, and that's liters times atm divided by Kelvin and moles. And this is going to be over our pressure, which was 1.7 atm. And so now I can go ahead and start canceling out units. So I have atm on top, atm on bottom, so my atm cancel out. I have moles on bottom, moles on top, Kelvin on bottom, Kelvin on top, and I'm left with liters. So I'm left with this variable right here. And that makes sense. I'm looking for volume. Volume needs to be in liters. So I know that my units are correct. I set my equation up correctly. So now you simply multiply everything, and you're going to get a volume of, I'm going to go ahead and write all the units out, so 34.87801 liters. However, let's figure out what we need our answer to actually be in. We have 2 sig figs right here, so we'll go ahead and put our answer in 2 significant figures because that is the lowest amount. So we'll end up with, so 2 sig figs, we could say 34, however, because there's an 8 here, we're going to get 35 liters. So 35 liters is our answer. Let's go ahead and go back here and move on to example 2. So it says, at a certain temperature, 3.24 moles of CO2 gas at 2.15 atm takes up a volume of 35.28 liters. What is the temperature in Celsius? So make sure you pay attention to that. It allows us to know that we have to do a conversion. So let's go ahead and go back to our boogie board to work this example. So we take our standard ideal gas law equation. So PV equals nRT. And we can convert this to what we're actually looking for. So we're looking for temperature. So we can divide by nR on both sides. So we get temperature equals pressure times volume divided by N times R. And you'll see kind of the same way I set it up before with my R value, how I had it to the side. I'm going to do that again because I just don't like the way it looks with having multiple fractions within fractions. So I'm going to show you how you can do it. You don't have to do it this way, but I'm going to show you how I set it up where I can set my R to the side and it still be on the bottom. So before we do that, let's go ahead and identify what our variables are equal to. So our pressure is going to be 2.15 atm. Our volume was 35.28 liters. Our N was 3.24 moles. Our R is that constant, so 0.0821 liters times atm divided by Kelvin times moles. And then temperature is what we're looking for, so that's our unknown variable. So let's go ahead and plug everything in. So we'll say our atm, or our pressure, so 2.15 atm times our volume, which is 35.28 liters. And you'll see what I do with my R in just a second. So I set this up like that. I say 3.24 moles. And then over here, I'm going to put my R value. So I have 0.0821 liters times atm. I'm just kind of flipping the way it normally looks because we need that R value, it's 8, we need that R value at the bottom. So I have my number value, let's see, it looks all squiggly, but that's an 8. And then so everything that was on top is now on bottom, everything that was on bottom will now go on top. So it's K times moles. So that's kind of how I set it up, or you can just plug it all in at the bottom. It's your choice. But it's nice and pretty now. We can start to cancel out. Our moles, moles, ATM, ATM, liters, liters. We're left with Kelvin as our unit. And again, that makes sense because we're looking for temperature. Our temperature needs to be in Kelvin when we solve for it. And then after we solve, we can always convert it to Celsius if need be. So once I have all my units canceled out, I can go ahead and just do my multiplication and division. You'll get a temperature of 285.1536 Kelvin. And before we convert it, I'll go ahead and move this to the proper amount of significant figures. We have 3 sig figs here, so this will be 285 Kelvin. And then if I want to find Celsius, it's going to be Kelvin minus 273. So we'll take our 285 minus 273, and we get a temperature of 12 degrees Celsius as our temperature. And that solves example 2. All right. So now we're going to talk about the ideal gas law and gas density. The density of a gas is directly proportional to its molar mass and inversely proportional to its temperature. So our gas density, which is going to be a lowercase d, is going to be equal to either m, which is the mass of the gas in grams divided by volume, or if they give you multiple units, it's going to be pressure times our italicized m, which is the molar mass of the gas, divided by RT, so our R constant and our temperature. The molar mass of the ideal gas is going to be our italicized m, because that's what we said it was before, equals our density times R times T divided by pressure. And your density is going to be in grams per liter. So let's go through an example. What is the density in grams per liter of a sample of SO2 at 932 mmHg and a temperature of 65 degrees Celsius? So we're looking for density. They give us our pressure of 932 mmHg, which we'll end up having to convert, and they also gave us a temperature of 65 degrees Celsius. So let's go to our boogie board so that we can begin to work this one out. Okay. So for this particular question, it would probably be best to use the longer equation. This is the italicized m, I don't know how to do fancy m's, divided by RT, where the m is going to be our molar mass of the gas. All right, so let's determine what our variables are. So our D, we don't know, that is what we're looking for. Our molar mass, we have to calculate. Our temperature is going to be 65 degrees Celsius. So just like in the other example, we're going to convert that by adding 273. And so we'll get a temperature of 338 Kelvin. Our pressure, we're going to have to calculate. And then our R value is going to be 0.0821 L times ATM divided by Kelvin times moles. So let's calculate our pressure first. So let's determine what this variable is right here. So we were given 932 mmHg. I like to set my stuff up on reaction tables. So I set it up on a reaction table. So the conversion between mmHg and ATM is going to be 760 mmHg. is going to be equal to 1 atm. So this is a good variable conversion to know, to be able to do conversions. So our mmHg cancels out, I do our math, and we end up with 1.23 atm. So that is our pressure, so that is what we plug in here. And then we determine our molar mass. So we have SO2. So we have, let's see, SO2 is our compound. S is going to be 32.1 grams per mole. This is just finding based off of the periodic table. Oxygen is 15.999, so I'm just going to round that up to 16 real quick. So we do 32.1 times 1 plus 16 times 2. And that will be what our mass is, because we have 1 sulfur, so we just say times 1. And we have 2 oxygen, so we say 16 times 2. So this will give us a weight of 64.1 grams per mole. So we say 64.1 grams per mole. And now we have all of our variables. So I'm going to go ahead and erase this real quick, and we'll begin to plug these variables into our equation. Okay, so we have density equals 1.23 atm, because our pressure, times 64.1 grams per mole, divided by, I'm going to go ahead and keep everything underneath so you can kind of see what it looks like when you plug everything just into the actual division problem instead of separating it to the side. So 0.0821 liters times atm divided by K times moles, and that's going to be times 338 Kelvin. So this Kelvin is below this division right here, so these cancel out, our moles cancel out, our atm cancels out, and what we're left with is grams over liters, which makes sense because remember our density needs to be in grams per liter, so we need G over L. So now we can just plug everything in. So you get a density equals 2.84 grams per liter, and that was just by multiplying and dividing, and you should get, you'll have a couple of extra numbers, but this is 3 significant figures. It's the smallest amount of sig figs, and so I just stuck with 3 sig figs right here, and that would be your answer. So let's go ahead and go back to our PowerPoint and move on to example 4. A gas has a density of 3.01 grams per liter at STP. What is its molar mass? So this one is a little bit different. We now have our density. We're told that we're at standard temperature and pressure, and we're looking for molar mass. So you have to use a couple different concepts here. Oops, sorry, let me go back. I'm going to move over to our boogie board so that we can work through this example. So we have our equation of m, which is our fancy little m, equals our T times density divided by pressure. So this is the manipulated form. We showed you this, but it's the manipulated form of our density equation, which is pressure times that little italicized m. It was just we rearranged it to be able to find what we're actually looking for. And we're looking for it at standard temperature and pressure. So let's find all our variables so we know what we have to plug in. So our density they actually gave us. They said 3.01 grams per liter. We're looking for our molar mass. Our temperature, this is where the STP falls in because they didn't actually give us a temperature to plug in. So we have to determine what that temperature is. At standard temperature and pressure, we have a temperature of 273 Kelvin. You can use the 0.15. I highly suggest you do whenever you're plugging it in for if you have Alex or Connect, whatever homework you have. Sometimes they want you to be very specific on your decimals. If so, make sure you do 273.15 here. Our R value is 0.0821. It's L times ATM divided by K times moles. And then our pressure, they also did not provide us with pressure, so we have to follow standard temperature and pressure. At standard temperature and pressure, our pressure is going to be 1 atm. So these two variables are what we used STP for, so our standard temperature and pressure. Here, let me move this in for you so you can see what I wrote. So those are the ones that we use standard temperature and pressure for. So now we have all our variables we can plug in to solve for what we need. So our M equals 0.0821 times liters times ATM divided by K times moles. That is times 273 Kelvin times our density, so 3.01 grams per liter. All of that over our pressure right here, so over 1 atm. We'll go ahead and start to cancel everything out. So ATM, ATM, liters, liters, Kelvin, Kelvin, and we're left with grams and moles. And that makes sense. Molar mass is pretty much the weight that you're getting from a periodic table. So it's going to be in grams per mole. So we have everything set up correctly. We're going to have the correct units. So now you simply plug it in, and you get a molar mass of 67.5 grams per mole. And that would be our answer. All right, now we're going to talk about mixtures of gases. So when we're doing mixtures of gases, we're going to be talking about our proportion of different gases within our total gas. So if we have like SO2, we can have a pressure of oxygen. We can also have a pressure of the sulfur. When it comes together, we have a total pressure. Gases mix homogeneously in any proportion. Each gas in a mixture behaves as if it were the only gas present. So they're going to pretend like they're there by themselves even though they're not. The pressure exerted by each gas in a mixture is called a partial pressure. So if I have SO2, we'll have two partial pressures. We'll have the partial pressure of the oxygen and we'll have the partial pressure of the sulfur. Dalton's law of partial pressure states that the total pressure in a mixture is the sum of the partial pressures of the component gases. So to find your total pressure, you just add up all of your partial pressures. So pressure 1 plus pressure 2 plus however many gases you have in that mixture, add all those together and you get your total pressure. So let's go through an example. What is the total pressure in ATM of a 10.2 liter container containing 45.7 grams of CO2 and 39.2 grams of CO with a temperature of 19 degrees Celsius? So right now we have two gases. We need to find the pressure of each of those two gases to be able to find our total pressure of our container. So, oops, let me go back, and we'll go over to our boogie board and work through this example. So we know that our total pressure is the pressure of our CO2 plus the pressure of our CO. And we know that we can find pressure by using the ideal gas law. So PV equals nRT, which would go to pressure equals nRT divided by V. So now we're using two different concepts to be able to find our answer. So this one is going to take a little bit of time. You have to break it down into pretty much three sections. Find the pressure of CO2, find the pressure of CO, add those two pressures together to find our total. So the first thing that we're going to do is work with the pressure of CO2. So the pressure of CO2 is what we're looking for first. So we're using this equation here, so let's go ahead and plug in all the variables we know. So we don't know pressure, that's what we're looking for. Our volume is 10.2 liters. Our temperature is 19 degrees Celsius. So we add 273 and we'll get 292 Kelvin. Our R is 0.0821 liters times ATM divided by Kelvin times moles. And then our N, which is our moles, is 1.038 moles. This you have to calculate, and the way that I calculate it is by 45.7 grams of CO2. This is what they gave us. Oops, sorry. And we're going to put it on a reaction table to convert from grams to moles. So I look up the molar mass of my CO2. It's going to be 44.01 grams of CO2 is equal to 1 mole of CO2. So our grams will cancel out, and we end up with 1.038 moles. So that's why I plugged it in right up here. And so now that we have that, we can plug everything in. So we say the pressure of CO2 equals 1.038 moles times 292 Kelvin times 0.0821 liters times ATM divided by Kelvin times moles, and this whole thing over 10.2 liters. So our moles cancel out, liters cancel out, Kelvin cancels out, and we're left with the unit of ATM. We're looking for pressure, so it makes sense. So multiply, divide, and the pressure for CO2 is going to be equal to 2.44 ATM. So this is part one. We now have one piece to our puzzle. So let me go ahead and erase this, and we'll work on the pressure for CO. So now the pressure for CO. Pressure, we don't know. Volume is the same as before, so 10.2 liters. Temperature is 19 degrees Celsius, so we add 273. We'll get 292 Kelvin. R is 0.0821 liters times ATM divided by Kelvin times moles. N is 1.399 moles. So again, I'll show you how I got that. So they gave us 39.2 grams of CO. We set up on the reaction table and find the mass, the molar mass of CO. That is going to be 28.01 grams for every 1 mole of CO. Our grams cancel out, and we end up with 1.399 moles of CO. So I just plugged that right in there. Now that we have each of our variables, we can plug in and solve for pressure. So the pressure of CO is 1.399 moles times 292 Kelvin times 0.0821 liters times ATM, and that was over K times moles, and this whole thing over 10.21. So our moles cancel out, our Kelvin cancel out, liters cancel out, and we're left with ATM. Makes sense, we're looking for pressure, so we're good to go. When you plug all of this in, the pressure of CO is going to be 3.29 ATM. So now we have the pressure of both CO2 and CO. So let me go ahead and erase this, and we'll solve for our total pressure. So the total pressure is going to be 2.44, which is the pressure of CO2, plus 3.29, which is the pressure of CO. So we get a total pressure of 5.73 ATM. And this is our answer. It's a bit of work, however, it's not too bad as long as you feel comfortable with using the ideal gas law. And that wraps up pretty much everything we're covering for gas characteristics and the ideal gas law. So let's do a brief overview of everything we covered. So we covered the ideal gas law, which was PV equals nRT. We went in depth on Boyle's law and Charles' law, where we just related the different variables and saw how one was inversely proportional, one was proportional. We talked about the density of gas, which is going to be density, I tried lowercasing this d, make sure it's a lowercase d, equals m divided by v, or P times italicized m, which was molar mass, divided by RT. That's going to be the density of a gas. And then if you're looking for molar mass of a gas, it's going to be the italicized m equals density times RT divided by P. And then finally, the last topic we covered was total pressure and partial pressure of a gas. So to find the partial pressure of a gas, you use the ideal gas law. And then to find the total pressure, you simply add those partial pressures up, and you'll get your total pressure. That's all I have for today. I hope this video was helpful, and I wish you luck on this topic. Thank you for coming.